In this lecture, we will see how to do cost targeting. We have already demonstrated the area target using the data available in table number 3. Now, with this problem, let us see how to do cost targeting. We introduce the stream data H1, supply temperature is 159, target temperature 77 and MCP value 22.85. The second stream H2, supply temperature 267, target temperature 80, MCP value 2.04. Third stream H3, supply temperature 343, target temperature 90 and MCP value 5.38. Fourth stream is C1, supply temperature 26, target temperature 127 and MCP value 9.33. The fifth stream is C2, the supply temperature is 118, the target temperature is 265 and MCP value is 19.61. So, this completes my stream table, which is shown in the lower part. We can match the temperature. Now, this is time to input the other data of the area targeting. So, we go to area targeting. The heat transfer coefficient of the first stream is 0.1, heat transfer coefficient of the second stream is 0.04, heat transfer coefficient of the third stream is 0.5, heat transfer coefficient of the fourth stream is 0.01, heat transfer coefficient of the fifth stream is 0.5. Now, we introduce the heat transfer coefficient of the utilities. The first utility, which is the heating utility, heat transfer coefficient is 0.05, and the second utility, which is the cold utility, heat transfer coefficient is 0.2. This finishes the heat transfer data. So, we say OK. Now, we go to the utility data and go for add, because we have to define the user definable utility. We press here plus then we put here data 360, the temperature, supply temperature of the hot utility, and here 359. Then we again press plus. We have to define the cooling utility. Cooling utility temperature is 20 here, and this temperature is 60. So, here we see that both the utilities have been defined. We can say OK. Now, we can see the composite curves with the utility. We have not added the utility, that is why it is not coming. We go for the combine. Now, we can combine the hot utility. So, this is the hot utility it is showing, and similarly we can combine the cold utility. This is the cold utility and this is the hot utility. We can say OK. So, it shows that the user defined utilities completely satisfy the energy requirements of the process. Do you want to show these utilities instead of the default utilities? We say yes. Now, it shows a composite curves with utility. We can see from here the composite curves with utility. Now, the problem is well defined. Now, we can go for the area target. We see the area target is given as this. We can define here the heat transfer coefficient. It appears to be, so the heat transfer coefficient is 0.5 here, and the second is 0.2. We say yes, OK, and see the area target now. The value of the area target is 4008.77. Now, once the area target is completed, then we can go for the cost targeting, in which we have to give the cost data. Now, this is the cost data which we will feed to the program. A, to calculate the capital cost target, if the individual heat exchangers cost can be computed according to a relationship. It gives you a relationship for the computation of capital cost, and that relationship is 30,000 plus 400 into area to the power 0.9, where A is the heat transfer area in meter square. And to calculate the total annual cost, the fixed cost as well as operating costs are required. So, there are two utilities, one steam and other is cooling utility, that is cold water. So, we have to provide both the costs. So, steam cost is $120 per kilowatt per year, and cooling water cost is $10 per kilowatt per year. Interest rate is 10%. Number of years, that is effective years for the heat exchangers, which is life of the heat exchanger is taken n is equal to 5 and Lang factor is taken as 1. So, details of this can be seen in any economic computation where the economic computation is given in any book, why this, how the Lang factor is used, or how the interest rates are being used for the computation of depreciation values. So, using this data, now we can compute the cost. So, to compute the cost, we go to again stream cost data. Here payback period is 5 years according to our problem, interest rate is 10% and Lang factor is 1. Now, for the stream number 1, the data is 30,000 and this is 400 and this factor is 0.9. Now, this is the cost equation, that is cost correlation. C is equal to A plus B, A to the power C. So, in our case A is 30,000, our case B is 400 and C is 0.9. Similarly, for stream number 2, again in our case this is 30,000, this is 400 and this is 0.9. For the third stream also we have, this is 30,000, this is 400 and this is 0.9. For the fourth stream also, this is 30,000, this is 400 and this is 0.9. Now, you can have different cost correlations for different heat exchangers. Here we assume that all the heat exchangers are in the same area range and made up of same material. In actual practice, the heat exchanger may be made up of different materials and their area range may be different. So, these values, that is 30,000, 400 and 0.9 may change for different heat exchangers. Here, to give you an example, we have taken the same cost equation for all the heat exchangers, but in actual this may not be true. In fifth stream, this is 30,000, 400 and this is 0.9. Now, we go for the utility. For the utility also, we have assumed that the heat exchanger costs can be computed using the same cost relationship, that is 30,000, here 400 and here 0.9. For utility number 2, this is again 30,000, this is 400 and this is 0.9. Now, this finishes our fixed cost computation part, that is data required for fixed test computation. We have seen how to feed the cost data to calculate the fixed costs of the heat exchangers. Now, to find out the total annual cost, the operating cost data has also to be fed in the program. In the operating data, the cost of the steam and the cost of the cooling water has to be given. So, this is the operating cost data in this part. Utility number 1 is the hot utility. Now here we feed the data, that is $120 per kilowatt per year, and the utility number 2 is the cold water. The value is $10 per kilowatt per year. Once we fill these two data, we have complete data available here with us. That is, operating cost is $127,742 per year, and the capital cost is $268,905, and total cost is $3,96648. Now once we have completed this, now we have the cost targeting value. Now this cost targeting value will change with delta T minimum value. So the next step is to see what happens when delta T minimum is changed, and what is the effect of the change of delta T minimum on energy target, on area target, on pinch temperature, on minimum number of heat exchangers, and on cost target. We will also see the variation of above parameters and the effect of heating consumption on the total area of network. So we can go to the diagram, we can go to the delta T minimum analysis, and we can go to the energy target. It says that what is the minimum value of delta T minimum you want to take. Here we have taken it to be 1, and the maximum value we have taken to be 50, and we want to generate 50 number of points in between. That means almost the addition is of 1 degree. So if I say it OK, I get a plot which shows me the variation of the hot utility as well as cold utility with delta T minimum. The other diagram which I can see is area target. In area target also, the minimum value of the temperature difference, that is delta T minimum, is 1, maximum is 50, and number of points generators are 50. Here it has given the other parameters. So if I say yes, then it shows the area target, that is how area is changing with delta T minimum. So we see that when the delta T minimum is increasing, the area is decreasing in this fashion. We can go to the third point, which is pinch temperature, and this pinch temperature is also changing with delta T minimum. So basically what we observe in this problem, that when delta T minimum is increasing, the pinch temperature is decreasing. We can go to the minimum number of heat exchangers. Here we see that how the minimum number of heat exchangers is increasing. This is a very typical phenomena which we are seeing. If the delta T minimum is up to 10, we have 6 number of heat exchangers. If it is from 10 to say around 30 or a little more than 30, then number of heat exchangers are 8. If it is around a little bit more than 30 to 40, the number of heat exchangers are 9, and when it is more than 40 to 50, the number of heat exchangers again drop down to 8. So it is a typical phenomena which we are seeing, which is obviously going to affect the cost of heat exchanger network. We can go for the cost target. In the cost target we have 3 targets: the operating cost, the capital cost and the total cost. If I show you the operating cost, see operating cost is increasing rapidly, it is increasing when I increasing the delta T minimum, and then little bit rate of increase decreases, and then again rate of increase decreases, but the overall fashion is that it is increasing with delta T minimum. Then I go for the cost target again for my capital, that is fixed cost. Here what I see that for heating and cooling the data have been changed. So, again I am changing it to 30,000, this is 400, this is 0.9, this is 30,000, this is 400 and this is 0.9. Say OK. So, this is how the fixed cost is changing with delta T minimum. We see that when the delta T minimum is increasing, the fixed cost is decreasing. And if you go for cost target and total cost, this operating cost has changed, this is 120, this is 10. So, here we see that this is total cost, which is changing with delta T minimum. Here we say somewhere here the minimum total cost appears, which gives you delta T minimum optimum, but a large flat portion is available here. That means when delta T minimum changes from this point to up to this point, there is no substantial change in the total cost of the heat exchanger. Then we can go to this more plots, and it shows that how the area is changing with heat consumption. So, we can see this, that shows this when the heat consumption is increasing, the area is decreasing. Now, after this we will take up a new problem to show the utility selection. When we are feeding the stream data, then in most of the cases, unless otherwise specified, the program calculates the utility values. Now, if we want different utilities, then we can feed these utilities, or if we want multiple utilities, that means 2 hot utilities or 2 cold utilities, we can specify it. Now, the question is that how to specify these utilities and what should be the amount of utilities. We will see that if we can specify the temperature of the utilities, hint can help you to find out the amount of these utilities. So, we take another problem, a new problem, and try to find out or try to see how the utilities can be specified. We go for a new problem. This is H1, this is 180, target temperature is 75, MCP value is 30, this is H2, supply temperature is 240, target temperature is 60, and the MCP value is 40. We can go to third, this C1, supply temperature is 40 and target temperature is 230. We can go for C2, the supply temperature is 120 and the target temperature is 300 and the value of Cp is 20. Now, this is our stream diagram, and if we see this, then we find that our heating duties are 1400 and cooling duties are 8150. Pinch temperature is 235, minimum temperature difference is 10 and minimum number of units required is 4. Now, suppose I want to specify utilities. So, in this, maybe that we should see the composite curve, then we see the grand composite curve. Now, grand composite curve looks like this. We need a lot of cooling and less heating. I can provide a hot utility here, one single hot utility, or I can provide two hot utilities, one in this level up to this and then from here to here. So, we will try to put two hot utilities and one cold utilities for this purpose. So, we go to the utility menu, we go for add, then we place here plus, then we change this to 315 and double click here 314, say OK. So, it automatically turns out to be a hot utility, and then we again press to enter a second hot utility. We enter the temperature to be 255 and double click here 254 and then press OK. Then we enter the third utility, which is a cooling utility. We give this temperature to 20 and this temperature to 30. Okay, once we finish this, this shows you the cold utility here. Then we go for combine. Now, we have already fed the hot utility 1 temperature ranges, that is 315 to 314, hot utility number 2 255 to 254 and cold utility 20 to 30. Now, we want to see that how much hot utility number 2 is required. So, we pull this slider and we see that hot utility number 2 requirement is 300 units. It shows you here, this is the line which shows you the hot utility number 2, and then we pull the slider of utility number 1, you will see that this line is growing. So, we see that it only goes up to 1100 and it satisfies at 1100, and 1100 plus 300 is 1400. So, which is the total amount of hot utility required. So, 1100 will be hot utility number 1, which is from 315 degrees centigrade to 314 degrees centigrade, and hot utility number 2 is 255 degree to 254 degree, its amount will be 300 kilowatt. So, it clearly tells that how much hot utilities are required at what level. We can go to the cold utility, because cold utility is only one. We see that its requirement is 8,150 kilowatt, and this is the cold utility line and this is the hot utility line. So, it shows that it satisfies, and here we see a combined composite curves with utilities. This is a composite curve with utilities. It looks like this. This is the ordinary composite curve, and this is the composite curves with the utilities. This is the cold utility from here to here. This is the hot utility from here to here, the hot utility number 2, and this hot utility number 1, which is from 315 degrees centigrade to 314 degrees centigrade. This is the hot utility, and the hot utility number 2, which is from 255 degrees centigrade to 254 degrees centigrade, is this. So, we see here the placement of 2 hot utilities and a cold utility. We can go for a grand composite curve, and in the grand composite curve we clearly see that 2 hot utilities are used. The first hot utility is from here to here, which is from 315 degrees centigrade to 314 degrees centigrade, and the second hot utility is from here to here, 255 degrees centigrade to 254 centigrade, and the cold utility is from 30 degrees centigrade, and it starts from 20 degrees centigrade and it rises to 30 degrees centigrade. So, this is the total grand composite curve with utilities, and if we want, we can see its area targeting. This is this, and then we can see other targeting values also. We can see the PTA for this, which shows the total utility demand is 1400 and total cooling is 8150, pinch is 235, and number of heat exchangers required are 5, and delta T minimum is 10 degrees centigrade. Now, this clearly shows if different utilities are to be used in a grand composite curve, then how to evaluate the amount of those utilities using hint. Now, in the next session, we are going to see, using the hint software, how a heat exchanger network is designed. First, we will go for a MER design, that is maximum energy recovery design based on the pinch rules. For this, we will take a stream table which is given here with 2 hot streams, hot 1 going from 720 to 320, hot 2 from 250 to 220, and cold from 300 to 900, and cold 2 from 200 to 550. So, this data we will take here the delta T minimum equal to 20. In earlier cases we have taken delta T minimum equal to 10 degree. So, we start our design, and this is a design which I am taking. Here stream splitting will be required. So, we will take two design problems. In the first design problem, we will exhibit how stream splitting is done, and in the second example, we will take a problem where stream splitting is not required. And then with the second problem, we will move forward and we will go for a MER as well as non-MER design. So, we start with addition of the stream H1, the supply temperature is 720, the target temperature is 320 and the MCP value is 0.045 megawatt. So, it will be in the kilowatt, this will be 45, and then we go for H2. This is from 520 to 220, and the MCP value is 40 in terms of kilowatt. 3 is cold stream C1, starts at 300 degree centigrade, goes up to 900 degree centigrade, and the value of MCP is 43 in terms of kilowatt. And then it goes to the fourth number C2, and the supply temperature is 200 and the target temperature is 550 and MCP is 20 in terms of kilowatt. So, if I say yes, so the stream table is generated here. The MCP 45, 40, 43 and 20. Now, this is my stream diagram, that is grid diagram, and my pinch is, hot pinch is at 520 degree centigrade, cold pinch is at 510 degree centigrade. That means my delta T is 10, but I have to take delta T to 20. So, I make it 20 and execute it. So, now the pinch temperature changes from 520, that is hot pinch is at 520 and cold pinch is 500. So, difference being 20 degree. Now, this is the grid diagram, and now I have to do the design part. Now, if I go for the stream and try to see the feasibility above pinch, then what I find that the rules are, this is process pinch, this is the above pinch, here I can change above or below pinch. So, I have taken above pinch. Now, my feasibility criteria rules are number of hot streams should be less than number of cold streams, and MCP of hot stream should be less than MCP of cold streams. So, here number of cold streams are 2 and number of hot stream is 1. Now, here we see that in none of the cases the MCP of cold streams are greater than MCP of hot streams. So, this poses a problem is created. I cannot match, and hence to do the matching, the hot stream has to be splitted into two hot streams, so that it satisfies the MCP criteria and matches can be put. So, we will try to break this. Here it is written double click on a stream to split it. So, I double click here. So, it tells if this stream is splitted, heat exchanger definitions introduced in this dialog box will be lost. Do you want to continue? I say yes. So, it gives you another table for splitting. Now, here it says the split stream number, this is 1, from temperature. So, it starts from 720 degrees centigrade and ends in 520 degrees centigrade. The branch 2 also ends in 520 degrees centigrade. Now, the division is I want 1 MCP at 40 and the second MCP at 5. So, the stream number 1 is now divided into two streams in the ratio 8.8889 to 11.1111. Now, the value of heat, that is delta H of the stream, is also divided. We see here it is 18,000. So, it is divided. So, let us place this. So, I say OK. So, it divides into two streams and numbers are given as 5 and 6, 40 and 5. Let us say yes, this is put here. So, this split stream is put here. Now, I can take this to this place and then can take this to this place. This is the ideal placing of the splitted streams, because above the pinch the stream is splitted, but not below the pinch. And this is the 520 degree centigrade. So, this stream, this should end at 520 degree centigrade, and that is why it was moved from this place to this place. Once this splitting is performed, now the placement of heat exchanger should start. Now, what I will do, I will go to the feasibility. It tells very clearly above the pinch it has been divided into 2, 40 and 5, 43 and 20. Now, this can be done because this satisfies, and if I want to see the feasibility, feasible matches, it very clearly tells that 2 can be matched with 5 or 6 and 3 can be matched with 6, and below the pinch 1 can be matched with 3 and 7 can be matched with either 2 or 3. This possibility it gives. It is a feasible match table. It gives all the possibilities of matching above the pinch and below the pinch. Out of this we have to select a few match, all matches cannot be done. And in the remaining problem analysis we will see that this matches increase or decrease the area of the heat exchanger network. So, selection of proper match is necessary, and the remaining problem table algorithm helps us to select proper matches. Now, once this is known, we can go to again feasibility and above the pinch, because we want to start matches above the pinch. And now, I want to match between these streams. So, what I can do, I can go for a matching like this, say 40 43 I can match, or 40 43 I can match, and 25 I can match. So, I click this, its color changes, and then it tells that click on streams to define the heat exchanger. So, if I click this and they say OK, a heat exchanger will be placed. We saw that a heat exchanger has been placed here. I can shift this heat exchanger to any place I like by clicking it. Now, what it tells, that the hot stream entry temperature is 720 to this, and exit temperature is 520. And here this heat exchanger starts from 520 and hits up to 686. Now, I can now go for a second match. I can go to this stream, feasibility, above pinch, and then I can click this and this. Then I click this and I say OK. A second heat exchanger is now placed. Now, this heat exchanger, which is heat exchanger number 1, transacts 8000 kilowatts, and this transacts 999.999 kilowatt, which is approximately equal to 1000 kilowatt. So, if you add these two, this is appears to be 8000 plus 1000, 9000 kilowatts. Now, I can go to the stream again, go to the feasibility below the pinch, and I find that there are streams here and if I see the table here, the rules are AMCP hot should be greater than AMCP cold streams, and number of hot streams should be greater or equal to number of cold streams. This rule is satisfied, and MCP of hot streams should be greater than MCP of cold streams. This rule can also be satisfied. So, this 45 can be matched with 43 or 20, and this 40 can only match with the 20. So, we see here that we will match the 45 with 43. So, if I place this, what it tells, MCP of what, sorry, this is 45 and 43. Say if I say this, so it gives a warning, these streams cannot be matched, feasibility criteria are not fulfilled. So, obviously, I see that the 40 is not greater than 43. So, it violates this rule, and hence it is not allowing you to do a match. So, I will go for 45 and 43. So, the color changes, that means it will allow me to do the match. So, I click this and I say OK, a heat exchanger is placed and its size is 8600 kilowatt. Now, I can match the 40 and 20. So, I can go. So, stream, visibility, below pinch. So, this 40 and 20 can be matched because MCP of hot stream is greater than MCP of cold stream. So, I click here, the color changes. I click here and I say OK. So, it is placed a heat exchanger which is heat exchanger number 4 and it transacts 6000 kilowatt. Now, what is left now? All major 4 heat exchangers has been placed and now we have to place the heaters and coolers. So, for this, here I have to put a heater, here I have to put a heater because this temperature 550 matches with this temperature. So, this is ticked off, these twos are ticked off and here 686 and 900, that means between this and this a heater has to be put up because this is a cold stream, it needs a heater and the capacity of the heater can be found out by multiplying, that is 900 minus 686 into 43, it comes out to be around 9.2 megawatt, that is 9200 kilowatts. So, I want to place the heater here. So, I click this stream and go to the heat exchanger and then I go for the add. So, it tells me that here that hot stream number 5 and cold stream number 2 are being matched here. No, this is not my requirement. So, I put add here. So, it gives me the 5th number heat exchanger because 1, 2, 3, 4 has already been consumed these numbers. So, the next number is 5th number heat exchanger. So, I put add. So, it gives me 5th number heat exchanger. But here it is given cold utility it is using and hot stream is this 1. This is not the case. What I will be using the utilities as hot stream and my cold stream number is 2. So, I will go here and make it 2, cold stream number 2, sorry I have taken 3, I took cold stream number 2 and here I go for utilities. Then I say that I will utilize this enthalpy. My enthalpy I can already calculate, this is 9200 and one of the temperatures I have to specify, it does not require I think any temperatures. So, I say so it demands a cold stream inlet temperature and this cold stream inlet temperature is 686. So, I can write down here 686 and then I say yes. So, here it puts a heat exchanger which is 9200. Now, due to the small calculation mistakes which may be after the decimal places, sometimes you get some thing from the software, some notification from the software that something is violating, but you can check it out and you can find out whether it is correct or not. So, now two cold units, that is coolers, has to be placed. Now, if we see this heater, this heat exchanger, the outlet temperature is 370, the inlet temperature is 520. So, 370 to 220, the stream has to be cooled down, and this will be cooled down using a cooler. Here also we see that the entry point is 320 here. Here the entry is 520 to this, the outlet is 328.9. So, you need to cool this down to 320. So, you need a cooler. So, let us place a cooler here. I click this, I go to the heat exchanger, then add heat exchanger. Now, in this I can press add. So, the heat exchanger number is now 6. My cold utility I will be using, and this is between the cold utility and hot stream 1. This is hot stream 1, and I will be using cold utility, and the enthalpy required is about 6 megawatt. So, 6000 kilowatts, and this we can calculate because this temperature is 370. So, 370 minus 220, this is 370 minus 220 into 40. This gives us the cooling requirement. So, I entered 6000. Here I entered cold stream temperature is not required. So, hot stream inlet temperature is, I can say the hot stream outlet temperature will be 220. So, I say OK. So, here I get a cooler 6 whose outlet temperature is 220 and the size of the cooler is 6000 kilowatt. The next is this, I have to put a cooler here. So, I click this, I go to the heat exchanger, say add, again I have to go add this is number 7 heat exchanger. This is between hot stream 1 to utility. This is a wrong information. So, my stream is 4th. So, I will take 4 as my stream and cold utility, and enthalpy required is, this is 400, about 400 kilowatts, and my hot outlet temperature is 320. Hot outlet temperature is 320. So, I place a heat exchanger here. It has not placed here, it has placed in the wrong place, 320. Now, it gives you a violation, a notice, but if you see that the violation is not much due to very calculations, we find is a very minor violation. If I make it 400, say 0.12 or so, this violation is removed. But this is a correct heat exchanger network which satisfies the almost all constraints. Now, here we have seen that this stream has been splitted, stream number 4, and this is what we get. Now, we can go for the heat exchanger network. We can find out the area. It gives you the area However, the area will not be correct because it takes the default value, and then based on that it calculates the area. But you can correct these values and you can have the correct area and the cost of the heat exchanger network. Now, if you go to the results, it almost tells you everything about the heat exchanger network. It gives you the temperature profiles of heat exchangers. You can see all the temperature profiles, how they look like, and then you can go for the specifications. It shows you the specification. You can change the heat exchanger and everything, you get it here. Then you can go for the area and cost. You can go for the results. In the results, enthalpy profile specifications results, here it shows you the inlet and outlet temperatures. You can change the heat exchanger and you can see these results. Thank you.